Hi, thanks for coming back. Do you hear me well? Speak louder. Louder? Hi, my name is Ignat, and today we're going to talk about sandboxing in Linux with no code. First, a little bit about myself. I work on Linux things at Cloudflare. I'm very passionate about security and crypto, and I enjoy low-level programming, kernel code, bootloaders, and other scary stuff. But today we're going to talk about sandboxing with a technology called SysSecComp in Linux. But to understand SecComp, we first will review system calls. So what are system calls? Nowadays we don't write applications on real hardware. We usually use some kind of operating system. And which is like a middleman between application and the hardware. And applications interact with the kernel using some kind of API. So these APIs are called system calls. So applications read and write data to this, send data over the network, always using some system calls. It's clear, right? So system call is a well-defined interface between the application and the kernel, and it provides some low-level abstractions and services to applications, file I/O, networking, time, etc. Also, the kernel enforces different access control policies to different resources from applications, as well as does some resource management using system. So what is SecComp now? SecComp is a Linux technology, and it's just another system call in Linux. But it is special in a way because it provides a way for an application to notify the kernel of its intention or other system call which it intends to use for its normal function. And then, it's like a contract between an application and the kernel, and then the kernel enforces this contract provided by the application. So basically, SecComp is not a sandbox itself, as Linux developers like to say. SecComp is a tool to create sandbox. With SecComp, the application can infer its intended usage to the kernel, and kernel then take actions to reach when this contract is breached. For example, this application may say that it will only use disk I/O, it will store files locally, but it will never basically send any data over the network, and then the Linux can enforce that policy for that application. So basically, why it's useful? Let's see an example. Imagine you're a developer and you're writing a simple clock application. So what a clock application needs from the kernel? So probably it only needs to know time, right? So basically in your SecComp policy, you can tell the kernel, hey, in the clock application, I will only use this system call, get time of day. And when your application functions normally, at some point it needs to know time. It requests time from the kernel. It's part of your contract. It's part of your promise to the kernel. The kernel will allow. But imagine you wrote your application in a low-level language, which is very unsafe, and somebody exploited your application and wrote arbitrary code in the future. What the attacker can try to do, they try to steal data from your computer, and for example, then they try to send this data over the network to themselves. And they will divert your clock application to use a send system call for that. But that is not part of your original contract, right? So the kernel immediately will kill the application and then prevent the data. So this is an example of a simple sandbox policy with SecComp. However, there are some challenges. How do we use SecComp in the application? So anyone doesn't know a Unix uname command, where you type your name and you get your type, the operating system you're using. So in this example, we will write a simple uname-like application which will use uname system call. There is also a system call called uname in Unix. So this is the full application source code. The important parts here is just we ask the kernel to provide some information and return that information to the user. Right? So let's see how it works. You can just compile this application, execute it, and it will tell you that your operating system is ready. So let's try to sandbox this application, and we'll just modify by adding another function called sandbox, and we will implement this function in this way. Now, I know it looks scary, but the gist here is we define our seccomp policy in this assembly-like language, and then basically the gist of the, like for the purposes of this exercise, we will define a bad policy. So we know our application needs a uname system call, but we actually prohibit ourselves to use uname system call in this policy to see seccomp in action. Right? So in this case, we basically, all this program, it allows every system call for the application except the uname system call. And what we tell in the policy, instead of just killing the application, we'll tell that if the application tries to use uname system call, return an error code. And we will use the funky error code Ignat down, like network is down. Like why would we need network for uname? Right? Yeah, and then we just provide this policy to the first. So let's try to execute it now. Yeah, if we execute it, we see that the application exited with error, and the error code is network is down. So we are now hitting this error pass here, and we definitely know we're hitting it because of our seccomp policy, because under normal scenario, like uname should never return Ignat down system. But as we just see, like the problem with seccomp tool is like this low-level assembly language. It's very hard to write, hard to manage, hard to update, and like we see, the code was huge for a simple application. Imagine real-world applications. How would that code look like, right? And we also need to be aware of different low-level details. We need to know the kernel system call numbers, architecture, because it's all different in the seccomp. So that's why, like, the community came up with a simplified library called libseccomp. We can rewrite our sandboxing function with the library. Now we see that the code is much smaller and simpler, and there are like 3 important pieces here. We define our default policy. We allow all system calls. Then we explicitly add a rule saying, like, if we try to use uname system call, in this case, we'll change the policy a bit to be more strict and tell the kernel just to kill the application. Yeah. And then we'll load the policy inside. So let's see how it works. When we compile this application, we need to remember that we also need to link to the library, because we now use the library. And if we execute this application, we'll see this like message from the shell that the application was killed with that system call message. But again, there is a problem, right? So in all these scenarios, I had to explicitly modify our application to add sandboxing support, right? So how do you think, like, how many developers start a project with this mindset? So, like, most likely I will write bugs and vulnerabilities. So the first thing I should do in my application is like provide like proper sandboxing support, right? Right? Nobody does that. Like it's all like shit features, users, and security is always like somewhere in there. Right? And yeah, and this is the problem with seccomp, that seccomp applies the rules policy only to the current process. So it is expected that application developers will add support for sandboxing to their application. But on the other hand, we have operators, sysadmin, SRE, who operate code in production, and they want applications to be sandboxed, but they don't have any control over the source, right? And also, like in big environments, you probably use some third-party proprietary applications, which you don't even have access to the source code, but you would like to sandbox somehow. So there is a gap, right? So on one side, we have application developers who can sandbox their code, but don't have the incentive. And on the other hand, we have like operators, sysadmin, SRE, security professionals who want to sandbox code, but don't have the ability. This is where no-code seccomp comes to mind. So how can you add seccomp support to an application without touching its source code? And this is like systemd, our favorite process manager, tried to do that. So if you run your application through systemd, you can use this system call filter directive in your unit files, and basically you can provide an allow list or a deny list of system calls this service or application should be using. So you basically can convey the seccomp policy to the kernel for the application managed by system. The link to documentation there. So let's try that. Let's basically recompile our original non-sandbox version of our toy tool, and we can run it with systemd, right? We see that it runs fine, we see the expected output, and we see that it exits successfully as 0 exits. Now we can actually sandbox it with systemd, so we will add this directive and prohibit this application to use the unique system call, and we'll see that it will be killed by the system, right, with a signal. We can also emulate the policy of returning custom error codes. So there is another directive here for that. So we can direct the application to return Ignat down error, and we will see that the name failed with network is down error code. However, there is a small print with this, the systemd approach. If you dig into the documentation, some system calls are always allowed. And this is because the way how systemd works, it always needs to allow these system calls to function properly. And one of the scary parts here is the exec-read system, which is always allowed even if you put it into the denial. So why is it bad, right? Let's go back to our clock application. When an attacker basically exploits our application and gains arbitrary code execution, what is the first thing an attacker will try to do, right? They will try to get a shell or execute some other binary, right? So they will use exec-read system call. So if your application doesn't meet that system call in its policy, it's very good to prohibit it. That's why we designed our own sandboxing tool. So it's a toolkit to inject custom seccomp policy rules into almost any process. It kind of works on top of the approach of systemd, but takes it one step further. With this, you can block any system call. So, and the toolkit actually consists of 2 components: a shared library for a dynamically linked application and a launcher for statically linked application. And it can block any system calls, including exec. And it works on any binary, written in any programming language, even proprietary binary. And it's open source. And you may say, hey, shared library, you said it's no code. Right? Why do we have to have a shared library? So it's a shared library, but it's special in a way that you don't have to program against it. You just need to use it in your process. So again, we will come back to our original simple tool, and with our toolkit, we can actually just provide custom seccomp policy, provide a deny list with uname system call in it, and all we need to do is reload the library from the toolkit into that process, and we will immediately see that the application will crash with that system call message from the shell. Yeah, so 2 things here. We just preload the library from the toolkit source code modification, and we provide our desired seccomp policy via environment. And nobody likes LD preload because it doesn't always work in all cases. For example, what if we just want to patch the application once and for all to add seccomp support? And we can do that. We can use the patch elf tool and just patch the executable file and add the library as a dependency to the application. Again, we don't need to modify the source code. We're patching the compiled executables directly. And then all we need to do is just to provide the second policy to the environment variable, and yeah, we can sandbox this code. What about static executable? So if we recompile our application with a static binary, this approach will not work anymore because there is no dynamic linker, deeper load has no meaning. That's why we have a second part of our toolkit is a launcher for statically built application. Instead of just launching the applications directly, we just launch it through our launcher here. And again, with the same environment variable, we can provide this custom second policy to any application. So yeah, Cloud for Sandbox tool, configuration by environment variables. The preferred ways to use an allow list, everything is denied except the allow system calls. It's hard to do. Then there is a deny list approach. You can deny specific system calls like exec v. And also there is another feature called default action. You can switch from basically just very strict action for the kernel to kill your application if it violates the second policy to just log the action, which is very useful for proprietary binaries. We don't know which system call it uses, so you can run the binary with the logging and actually see what it needs for normalization. Yeah, and the sandbox tool contains of two components. There is a lib sandbox library for dynamically linked applications, and you need to preload this library to the process address space or patch the elf binary directly. And there is a sandboxified launcher, which can be used for also statically and dynamically linked applications, and you just need to run your executables through the launcher. But at this point, you may ask also, why do we need, like, if the launcher works for dynamically linked application and statically linked application, why do we need the preloaded library? Why we can't always use, like, the launcher for any type of that? And to understand that, basically the difference, let's, from a, like, 1,000 feet view, review any code startup on the operating system. So when you launch an executable, usually there is some kind of a runtime init stage. Like every language, every framework has some kind of a runtime init stage, including C language, Java, Go, whatever. And then there is a stage of the main application. This is where your main function starts to execute, right? So runtime init stage is invisible to the developer. It's like added by the compiler and the linker, the application relations. Yeah, and in terms of sandboxing, if you use the launcher, the second policy will be enforced before the runtime init stage. And if you use the preloaded library, the second policy will be enforced after the runtime init stage. But what is runtime init stage, right? Runtime init stage is basically a lot of system calls which are never used afterwards in the application. So there is like memory setup and maps and protects, etc. And your main code might not need them in the future. So it would be nice to actually block them when your service operates in production. Right? And basically applying the second policy a little bit later allows you to have a tighter second policy there. So yeah, in this case, we only need to allow system calls from the main logic, and in this case, we also need to allow system calls from the runtime init. So again, let's see an example of our application. So now let's try, instead of a deny list approach, to switch to allow list approach. What is the minimum number of syscalls we need to allow for our applications to run successfully? And in this case, like if we use the dynamic library approach, we only need to allow 4 system calls for the application to function properly. If we switch to the launcher mode, the same application requires us to allow 13 system calls to function properly. So it's 4 versus 13. So this, if you have a dynamically linked executable with a dynamic library, you can have a much tighter policy for your application and data. Yeah, I think that's it, basically. Here are some useful links. If you didn't understand anything of our told you today. There is the version of this talk in the blog post here, and another link is the actual source code for the toolkit. You can grab, compile, and provide feedback, and maybe even pull requests. Yep, thank you very much. Questions? Questions? Yes, please.
Does a ability to wildcard exist? So what I was thinking was that if we write our own software, sure we'll know what syscalls we're using most of the time. It will be well, but especially third-party software, we don't know what it does. Being able to just trace all of the syscalls by just wildcarding and saying disallow all of them, but don't kill the process, just report it to us to create a list of syscalls being used that we can then sandbox. Is that a thing?
Yeah. Let me find this slide. Yeah, this is what this default action is about.
Yeah.
So if you want to run in this like discovery mode, so what we need to do is you create a allow list with no system call, so you deny everything, but you also switch this default action to log, and then you can monitor the system log, or if you use audit D, it will be logged in the audit logs that an application violated the SecComp policy and which system called it. Then you can parse these logs and actually identify which system call is being used by this proprietary piece of code. Yeah. Yes?
Sorry, you apologize for this introduction, but since we started building applications which are containerized or very small things, they do a small function as an application, for example, the database or the application itself. Is it within best practices to actually limit the system calls at the container level itself, or because the tool itself is more about the application, isn't it? Is it in best practice to just limit the system calls at that container?
Yeah. So containers also use SecComp as well. So like many container systems, like Docker, Kubernetes, they have some kind of a default safe system call policy. It's quite wide, but you can actually, for most of them, you can specify your own custom SecComp policy. And you can like shrink it down. Still, the fact that basically, but in this case, it's the same as with runtime init stage, right? So what I'm trying to say is, now people don't build very slimmed down containers with only one binary. They're still kind of fat. You have some basic file systems and stuff. So you have this fancy runtime init stage, right? So I think the best approach is to have actually both. Because SecComp policies in the kernel, they are stacked, so you can sandbox yourself, but then you can like shrink it down later if you need to. So for example, when your container application starts, you have a wider SecComp policy defined in the container runtime for your application to actually allow it to start. Go through all the bash commands and pre commands you need to actually start the service. And then once your main code is started, you can use this tool to further like narrow that the attack surface by narrowing down the allowed syscall just for your main code. Going once, going twice. So.